So, welcome back to the course on digital signal processing. We are into lecture 1 today and we will discuss the basics of this subject from this lecture. So, let's begin. Okay, let's first see what are the topics that we shall be covering in the lecture. Okay. The first is we'll be understanding the definition of signals. Okay. Next, we will deal with continuous and discrete time signals. What is a continuous signal? What is a discrete time signal? Then we'll look into how do we convert, how the conversion is brought about from a continuous time signal to a discrete time signal. How do we convert that conversion? We shall also discuss on analog and digital signals. We'll also understand how do we convert analog signal to digital signals. Okay, so we'll also be discussing about how do we bring about the conversion from analog signal to digital signal. And we'll also understand finally what do we mean by quantization. We will also discuss the concepts of quantization in this lecture also. So what is a signal basically? Now, as you know, you have a basic idea about signals and systems. So anything that carries information is a signal. And we can also say that any physical quantity which varies with some independent variable, that can also be a signal. We can also basically say that there are two or many other types of signal depending on how many independent variables does a signal depend on. So if the signal depends on a single variable, then we call it a one-dimensional signal. But if the signal depends on more than one variable, then it is called a two-dimensional signal. One-dimensional signal, you can take for example an AC signal is a one-dimensional signal, and on the other hand you can say that an X-ray or a picture signal is a two-dimensional signal. And there are some examples that I said: ECG signal, EEG, electroencephalogram, speech signal. Okay. And signals, oh well, obviously we have an idea, we have a misconception in our mind that signals always mean electrical signals, but it is not so. Signals, in this case, it can be anything which carries information. Even the money that is deposited every month in a savings account, that can also be a signal. You will be surprised to note that. Okay. Now, what are the types of signals? Now, there may be different types of signals and there may be different modes of classification of signals, but we'll restrict ourselves here to the basis of continuity along the time axis. So based on whether a signal is continuous in the time axis, we have two types of signals. One is called a continuous time signal. Continuous time signal is continuous in time, but it may not be continuous in amplitude. Okay, so example, speech signal, the ECG signal, all these are examples of continuous time signal. Discrete time signal, so they are discrete in time. Discrete in time means the signal is defined at discrete intervals of time. We'll see the diagrams. We'll look into this type of signal with the help of a diagram. Now, this discrete time signal, it also means the amplitude of the signal may or may not be continuous. Continuous means the amplitude can take any value. Okay, so if the amplitude is restricted within some values basically, then we can actually say that it is a discrete time signal. Okay, so if the amplitude is restricted or it can take only some defined range of values, we say that the amplitude is discrete. Okay, but otherwise amplitude is continuous. A basic example, as I told you, the temperature which is measured over a period of time. Say if we are to measure temperature after every 1 hour, Say at 1 p.m. I measure the temperature of the room, at 2 p.m. I measure the temperature of the room, and after every 1 hour I try to measure the temperature of the room. And obviously the temperature, say at 1 p.m. I note some particular temperature, at 2 p.m. I note another temperature. Now in between 1 p.m. and 2 p.m. I do not know what is the temperature in the room. So that is a discrete time signal. And obviously savings account, the money that goes into your savings account every month is a discrete time signal. Continuous time signal. So a continuous time signal is defined for every single instant of time. For every time it is defined. Okay, means if there is any value in the time axis, there will be a corresponding value on the y-axis. It is denoted by xt. T is the time index, and every value of time has a corresponding value of amplitude. And basically continuous time signal is, the word continuous here implies that you are drawing the signal without lifting your pen. Okay. And this is the basic diagram of a continuous time signal. It's a basic example of a sinusoidal signal that you can see over here. Okay, which is continuous in time, so you're not lifting your pen while you are drawing the signal, drawing the basic signal. Okay. Coming to discrete time signal, or DT. So they are defined for discrete instants of time denoted by xn, where n is the time index. The values of the signals are defined at discrete time intervals, but in between the time intervals the signal values are undefined. Okay. So let us look into it with the help of an example. So this is a discrete time signal, as you can see in the diagram. So at minus 20, minus 10, so you can see that there are gaps between the signal values. So in those gaps, in those spaces, the values of the signals, as you can look into my mouse, so see there's a gap in between over here. Okay, so the gaps or the spaces in between the signals, the value of the signal or the amplitude of the signal is not defined in those gaps or in those spaces. Okay. So this is the good example of a discrete time signal. So if we can just simply convert that sine signal, if we do it in this form, if we represent this in the discrete form, it looks somewhat like this. Okay. Now, how do we convert? How do we convert a continuous time signal to discrete time signal and vice versa? So basically it can be done through sampling. So sampling is a process by which we can convert a continuous time signal to a discrete time signal, and sampling means that we hold the signal values at specific time instant, and the rate at which we sample, which is called the sampling rate, that decides whether we can reconvert or we can get back the original signal or not. The conversion of the sampled signal back to the original signal, so this process is called reconstruction. So discrete time back to the continuous time is called reconstruction. Now reconstruction may be possible, may not be possible. Reconstruction is decided by the sampling rate of the signal. Okay, so obviously we'll discuss more about sampling in some later topic at a later time. Now, how do we sample a continuous time signal? So this is a good example that you can see, a diagram by which you can see that we have a continuous time signal and that is sampled at specific instants of time. Say after every 1 second of time, we are trying to hold the value of the signal at that particular moment of time. So in between 1 and 2 or in between 3 and 4 or 4 and 5, I don't know what is the value of the signal. So this is how we sample a continuous time signal into a discrete time signal. Now, analog and digital signals. So analog signals and digital signals are based on the values that the signal take in the y-axis. So analog signal is a continuous, it may be continuous in amplitude, but it may or may not be continuous in time. So a discrete time signal may also be an analog signal. For example, the temperature that is measured from an analog thermometer. So the amplitude is fixed, means the amplitude can take any value in case of an analog signal. But in case of a digital signal, the amplitudes are discrete. The amplitude may not, they take only a limited range of values. For example, the temperature that is measured from a digital thermometer. So what about digital signals? Now digital signals can only assume some defined range of amplitudes. I give you an example. Say the temperature of the room, say your body temperature, say it's about 37.2 degrees Celsius. Now if it is measured on an analog thermometer, you can find out the exact values based on how it is calibrated, 37.2. But if you try to find this temperature on a digital thermometer displays a value of 37 degrees Celsius, provided that digital thermometer has got only 2 digits over there. So if the digital thermometer has got only 2 digits, it will truncate that 0.2 and it will only show you 37 degrees Celsius. So that is a problem in case of digital signal. So in case of a digital system, there is some error you can see that is introduced in the system. This is called quantization error. And a digital clinical thermometer can assume only integer values on the Celsius scale. And digital systems basically generate digital signal. And binary signal, as you know, it's a very special case of digital signal where only 2 values are assumed. Either it can take the value of 0 or it can take the value of 1. Okay. Now, how do we convert analog to digital signal conversion? How do we do the conversion? First is that it is achieved by quantization in an analog to digital converter. So first thing is that basically there is a process which is called quantization, by which an analog signal is converted to a digital signal. And here quantization, what it does is that it defines the amplitude, it defines certain amplitude levels which are called quantization levels. Okay, we will see a diagram also. Now signal values which are close to that quantization level is assigned that level. Okay. Quantization involves an error which is due to an approximation, because there is a truncation, there is an approximation while we quantize a signal, and there's an error which is introduced which is called quantization error. And this error can be reduced obviously by increasing the number of levels. If you have more number of levels, more number of quantization levels, then the quantization error will be reduced, but at the cost of increase in the cost of the system. The system cost will increase a lot. And quantization step is the difference between the quantization levels. For example, one quantization level is at 2 volt and the other quantization level, the next quantization level is at 4 volt, then 6 volt. So the gap between any 2 consecutive quantization level is called the quantization step. So in this case, the quantization step will be about 2 volts. Now if we want to have greater accuracy, then you can reduce the you can reduce the difference between each quantization level. Okay. So quantization, you can see that this is the diagram by which we can quantize a system. And it's very simple. You can see that there's a continuous time signal which is given in the blue line, and the red line, the maroon line, tries to catch up with the signal. So based on certain rule, whenever say 0101, 0110, 0111, so these are certain quantization levels, okay, up to which the through which the signal is actually quantized. So based on where, if the signal is near to some level, then it is then the signal is assigned that particular value. And obviously you can see that how a continuous time signal has got a tracking error in this case. So a brief summary. So signal is anything that carries information. Continuous time signals are continuous in time. Discrete time signals are discrete in time. Continuous time signals to discrete time signals can be converted by sampling. Analog signals are continuous in amplitude. Digital signals are discrete in amplitude. Analog signals can be converted to digital signals by simple process of quantization. So this is a basic summary of what we had done in this lecture. So if you have any queries, any doubts, please do mail me on this mail ID. I will get back to you with my response. Thank you so much.